All right, so here is a data, a table to show these are ionization energies. So judging by this, which group is the thing in this atom? Which group is it in? So to guess that, we'll have to look at where is the biggest jump. So right now, the biggest jump that we see is right after the very first one, because the jump is almost the 10 times the energy required. So we'll say that this is electron in the very last level. So this is in first shell. Okay. If I were to make a graph of this, roughly this would be another. So here's another graph. Judging by this graph, can you say which group the thing is in?
Group 3.
Group 2 actually. Period 3.
Oh.
Group 2, because in the last shell, the third shell, the one that you're removing first, there are only 2 electrons. And this time, instead of having the regular values, we are using log values. Log values make it easier to show them, because now you're dealing with powers and not anything else. Which group is it in?
Is this also in 2?
Yeah, this is magnesium, because it has 12 electrons overall, and it's in group 2. Okay, how about this one?
Group 4?
Group 4, yes. It is group 4 because these 4, they're in the last shell. Then there's 8, and then there's 2. So the configuration is 2, 8, 4. And that means it is silicon with 14 protons. Okay. Now, sometimes we also want to write equations to show how we are removing energy. So, for example, if this is a question, write an equation to represent the fifth ionization energy of fluorine. Now, that means you're removing the fifth electron, which implies that you have already removed 4 electrons. So we'll start by saying that we have fluorine, that's not good. And we have removed 4 electrons from there. And that is changing to fluorine with 5 electrons removed, with 1 electron separated from it. And that is how you write ionization energy. Better
So
yet,
why did we write an E with F on the right side?
because it shows that here it was together and here it is separated. The plus is like a comma.
But why do we write FE5?
Oh my God.
Why not
I
just
should have written F. It was F. Here's a question. These values are given. Now the examiner is like, explain the general trend. What's the general trend?
They're increasing the ionization.
Overall, they're increasing. That's the trend. So why are they increasing? Because you're going from left to right in the periodic table. If you look in the periodic table, and sodium is on the left, then it is magnesium. So sodium, magnesium, aluminium, silicon. That's how you're going from left to right. And when you go from left to right, 2 things happen. Size decreases because nuclear charge increases. So it pulls the outer shell at the same time. And because they're in the same period, that means same number of shells, which means shielding effect is roughly constant. So the only difference that's happening is because the electrons are getting closer to the nucleus because the size is decreasing. So that is why energy is increasing overall. That's the general trend. But why is the energy of aluminium here, why is it decreasing here? That's the next question. So explain the why aluminium has a lower first ionization energy than magnesium. So for that, we'll have to look closer into the structure of aluminium. And we'll answer that question at the end of today's lesson when we are done with the electronic configuration. Electronic configuration, we can use ionization energy as a trend to show what electronic configuration is and how it goes. So large increases, whenever you say, those predict the group. So large increases like over here show that, like here you can see this is a large increase. This is a large increase. This increase shows. So whenever you see large jumps or large increases, they predict the group of the element. So for example, this one, as you saw, this is 2 big jumps. So that shows that you have 2 major changes in the shell. So this is the first shell, this is the second shell, this is the third shell, and that's how they go. But then there are smaller changes, and those smaller changes show how the electrons or how the arrangement varies from one to another. Let's go on to shells today. Let's see what shells are and how they. So far we know that we have at the highest level, we have these energy levels, and these levels are discrete, they have fixed numbers. And this is a rough idea of what they might be like. So the circle is supposed to show that they are moving around the nucleus. And this is the nucleus here. And these are shells. So n equal 1 means the first shell. And lower number means lower energy. So energy increases outwards. So the ones that is bigger or the one with higher charge has higher energy, as you know already. And you can see that they are getting closer and closer. The difference between 1 and 2 is not as big as the difference between 2 and 3, or the difference between 3 and 4, and so on. So they get closer and closer, which means the difference in their energy, the energy gap, it starts to decrease as you go up. Now, every one of these, they have subshells, and the subshells are same as how the number of shell. So for example, when the first shell has just one, which is S, second shell has two S and P, third has S, P, and D, fourth has S, P, D, F, and that is how they continue to go. Now the energy, it increases. So that means that you can kind of show this as one, the first one has one shell, subshell, the second one has two subshells, third one has three subshells, and fourth one has four subshells. And that's how the energy increases. Okay. So each one of these subshells accommodates electrons, and these subshells themselves have orbitals. Now, the way their energy is, pay attention to this graph for a minute. So this is supposed to show how their energy increases. So every shell is in a different color for clarity. Now, if you notice here, you can see that 1s and 2s has a big gap, and 2s to 2p is a gap. And then obviously there's an equivalent gap between 2p and 3s. But between 3d and 4s, the gap isn't that much. And not just that, 4s is at a lower energy level than 3d. And mind you, these are empty. Just like that, 5s is at a lower level than 4d, which means that electrons, which we know follow off-bar principle, which is like building up. So that means they're going to first fill the shell number 1, then cell number 2, and within cell number 2 they're going to go for 2s, then 2p. Within 3 they're going to go for 3s, 3p, but next one is 4s. They're not going to go into 3d. They're going to go into 4s because it has lower energy than 3d. It doesn't matter which shell it is in. So they always prefer lower energy level. So that is why 4s you will see is filled first, 3d is filled later, 5s is filled before 4d, and that is how it goes. In AS, we are going to limit ourselves up to 4p, and that's what we are going to just be limited to. Now, every one of these subshells can accommodate a certain number of orbitals, and every orbital has one pair of electrons. So how many orbitals? They are in odd numbers. So 1s has one orbital, which we show as a box. 2s has one orbital because s always has one orbital. P has three orbitals, which we show as three boxes. Then again, one box for s. 3p has three boxes. 4s is one. And then 3d is the third odd number. So that is 5. That's how they go. Similarly, 4p has 3, 5s has 1, 4d has 5. That's the odd number, third odd number. And every orbital can have one pair of electrons, which means the maximum number of electrons that you can fill into anything is basically given by the capacity of orbitals. So this is what the capacity is. And you can see clearly that S has one pair, which is 2. P has 3 orbitals, so 3 pairs, 6 electrons. D has 5 orbitals, 5 pairs, that is 10 electrons. And F has 7 orbitals, 7 pairs, 14 electrons. Okay, so that is the basic capacity of these subshells. And this is fixed. This is like fixed in nature. Now you can go back to O levels and feel like, all right, in O levels you said first shell only has 2 electrons. And why is that? That is because first shell has just one S, and that one S can only accommodate one pair. And there you go. That is the reason first shell can only have one electron, because it has just one subshell, and that is S, and that has one orbital which can accommodate one pair. So that's why 2. Similarly, we said the octet rule, if you remember. Octet rule was that they will fill 8 electrons first. And why is that? Because in the second orbital, you have 2 and 8, 2 and 6, which make 8, because 2s has one pair, 2p has 3 pairs, total 8. Similarly, if you go to third electrons, we saw that we have 3s, which is one pair, and 3p, which is 6 electrons. Total is 8 again. And after that, we used to go for, whenever we were to draw potassium, we used to tell students that even though it can accommodate 18 electrons, it will still go into the fourth shell. And every teacher I've seen, they have their own variant of how they tell it to their students, because students are inquisitive. They want to know the real answer sometimes, and we are limited by the syllabus. But now we don't have that restriction. So as you can see now, the reason they go into 4s and not 3d, even though third shell can accommodate like 18, but they still don't go there, is because the third shell has 4s to be filled first. So before it goes into 3d, it has to fill 4s, which is why you will get to calcium with 4s2 and 2 electrons in 4s before you start with scandium, which is in the third shell 3d, which is also the reason in O levels we restrict ourselves to just first 20 elements, because they are where 4s is filled. So octet rule breaks after that, kind of breaks after that. Okay. So what is orbital? Orbital is the region in space where electron has a high probability to be found. If you were looking for electron, the boundary of an orbital is where you have a high chance of finding it. Okay. And these orbitals, they have shapes. These shapes are given by their wave functions, but Schrodinger equation helps us find that, but we don't need to go into that. Okay. So that is way beyond our syllabus. So we just need to know that S is sphere, P is like a lobe like this, and D has 5 of these, which are like butterflies. Now, P's lobe occurs in 3 axes, X, Y, and Z, so it is along the axis. And butterflies are either between the axis or along the axis for D. So there are 3 of them between the axis, because we have 3 different axes. And then we have one along X and Y axis and one along Z and Y axis. So this is the shape that we have for these orbitals. And this is where you have a high chance of finding these electrons. There's another rule that we sometimes tell students. It's called Hund's rule. Hund's rule simply says that electrons don't like to pair up. So if they have a chance to stay individually in an orbital, they will do that. And that's pretty intuitive. So today we're going to do electronic configuration. You will see how that works. So what I have here right now is an empty atom, but instead of having it like the shells, I have broken it down into these subshells. So what I'm going to do is I'm going to fill electrons and try to figure out how they will fill this atom. So help me out here, you guys. So this is an empty orbital, empty atom. You put the first electron in there. Where should that electron go?
In 1s.
1s, because that's the lowest energy level available. And it can have any of the 2 spins. It can be up or down, but we usually show it as up. Again, that does not mean it can't be down. It can be, but then there's not much of a difference. Second electron, where should it go?
Again in 1s.
Why?
Because उसमें और कोई है ही नहीं orbital.
इसमें है 2s है 2p है, ये सारे orbitals available है.
In the fresh shell.
Yeah, that's the lowest energy level available. The technical word is it's following off-bar principle. that they fill the lower energy level first. But when it goes there, it's going to go like this. We are going to show it as a downward arrow, show it has an opposite spin. And now the third electron, even though it wants to go to the lowest energy available, the only availability is in 2s. So right now, whatever we have filled, we're going to write this as 1s2. The third electron, where does it go? 2s. And then it goes this next one again in 2s, but opposite spin. So we write that as 2s2. Fifth electron, where should that go?
In 2p.
2p. Which of the 2p ones? First, second, or third?
Anyone. I think first.
Anyone. That's the right way. Because all of them are identical in terms of energy. So it doesn't really matter which one it goes to. And again, we show them as it goes in the first one first. Where does the next one go?
In the next box. 2p में.
Why the next one?
Because you said they
Why
don't-
not fill
they
this
prefer
one?
to be like separate.
And why is that?
Off bow.
No, that's not alpha, that's Hund's rule. But again, why is that? That is because when it comes over here, there is some repulsion that it will feel from the electron that's already there. But in the next one, there's not that repulsion. There's no such repulsion. That's why it goes over here. It avoids that extra repulsion.
So this Hund's rule is that the electrons are gonna fill up the orbitals individually first before pairing up.
Yes, it's called Hund's rule of maximum multiplicity, which basically says that they're going to fill multiple orbitals before pairing up. Yeah, so that's what it means. So the next one is obviously going over here. Now, so far, where have we encountered some jumps for what you call, what's that? Ionization energy. The first jump is going to be over here. Then there's one going to be over here, but it's not going to be that significant. And we are now going to encounter another one because now we are going to fill another electron that's going to pair up in any one of them, by the way. And when it pairs up, it simply means that it's going to feel some repulsion. It is going to be easier to remove this electron. And obviously the next one comes here, the next one comes here, and you will see another jump here. Because now you're changing a shell, big jump. Now it goes here, here, small jump, again small jump. Because you're changing a shell, but it's going to go into 4s now. 1, 2, small jump. And now it's going to go into 3D. We are going into scandium now. So scandium is one here, one here, one here, one here, one here, and then small jump and starts to fill in there. Okay, that's how they fill up. So then this and this. Okay, so that is how these fill up. Now, how do we write this? Now, by the way, there are some extra rules that we haven't talked about so far. For example, now I want to remove these electrons. Okay, because remember, ionization energy is all about removing electrons. So let's see which electrons are easier to remove and which one are difficult to remove. Right now, this is a very stable atom, 4p. It is actually a noble gas right now because all the orbitals are filled up. It doesn't want to lose these electrons. So it's going to offer a lot of repulsion. So removing this electron right now, it's going to be hard. So you are going to apply a lot of energy. Now, which electron will be removed first right now if we do that?
Will it be from 4p?
Yes, it will be from 4p, the outer one, but any of the 6. It doesn't matter. They're all identical. Usually we just remove the last one. So there you go. And now the next one is not going to be that hard to remove because this subshell is not that stable anymore. One more, one more. And now it's going to get the stability that is associated with half-filled subshell. The half-filled subshell has some stability that it don't lose. That is why when you remove the next electron, it's going to offer some resistance. So removing this electron in particular is going to be a little harder.
Where do full filled and half filled, they have like the same amount?
So here's how it goes. The high stability comes with the full shell, then full subshell, then half subshell.
So full shell would mean like all the fours.
Yep. So that's how it goes. So now we are going to remove this one. Easy, easy. The next one is going to be hard. And here's another thing. Once 4s is filled up, it doesn't stay here. It actually stops being here and goes to a level that is above 3D. After being filled up, 4s has a higher energy than 3D, which is why when you next remove electron, it's not going to be removed from 3D, it's going to be removed from 4s. One, quite a lot of repulsion that you're going to face, but this one's easy to remove. And then this one, kind of difficult to remove, but after that it gets easy. 1, 2, 3, 4. And now you have a half filled subshell, difficult to remove. So it offers some, you're damaging the stability. But once that is done, 2, 3, 4, 5, shell is empty, subshell is empty. Now again, full stability, you get the idea. Every time you have a full subshell, is going to offer some resistance. You're going to have an increase in electronegativity. But every time you're going to change that, every time you're removing an electron from something that's not that stable, it's going to be much easier to do that. So that is how it goes. So you keep on removing them like this as you fill them up. And that is the electronic configuration. How do we write this? It's simple. Whenever you want to write it, you fill all of this and then you're like, okay, for example, right now I'm seeing 2s2, 2p6. The next one, if I had this one, I'll be write 3s1. Okay. So as your homework today, write in this form and draw in this form electronic configuration for first 20 elements. Go on, do that. In the next class, we'll talk about transition metals, some of their peculiar properties, and how that happens. Okay.
So when we're writing the configuration, do we write
Yeah.
3D first or 4s first?
So examiner does not penalize you if you do 3D first or 4s. But if you're writing in terms of energy, then after they're filled up, 3D comes first, 4s comes later, because 4s has higher energy after it fills up.
Okay.
Yeah. All right. Take care.